Okay, thank you everybody for coming. I'm happy to introduce Professor Benny Seibold at University of Temple. He's associate professor of mathematics, and he is the director for the Center for Computational Mathematics and Modeling at Temple. And he's a longtime collaborator with many people on this project. Thank you. Go ahead, Benny.
Thank you, Sean, and thank you everybody for being here. So yeah, it's my job to close this up. So I'm trying to be, on the one hand, a mathematician and provide some math on this, but on the other hand, also provide somewhat of a more conclusive message on many of these things. So specifically, the goals essentially and agenda of this presentation is that over the work of many of the exciting things that happen on this project, people have used energy models in different form in all kinds of things. Specifically, of course, exciting in using them in the reinforcement learning work done by the RL team, and have reported lots of observations. What happens when you put energy in as either an evaluation criterion or even an optimization criterion in your reward function. And there's always this persistent question also around, well, if we program our vehicles to do wave smoothing and regularizing the flow, is that actually the same as energy optimization, or is it sometimes not? And the goal of this talk is to explain some of these questions in terms of looking at the principal structure of energy models, how they could come, and how this interacts then when you think of energy optimality. So we're going to start by just talking a little bit again about modeling the energy of a single vehicle, then talk about what happens if you want to optimize the energy of this vehicle, and then what are the lessons from there, and of course, what does it mean for the bigger theme of having traffic flow rather than a single vehicle. So, so to start on single vehicle energy modeling, the energy models of vehicles, in principle, I would say can be classified in three types of approaches. The first type is principal physics-based that are really treating the vehicle as almost like a point of mass, and say, okay, my energy function ultimately is based on some power function that is dependent on the vehicle mass. Here, can you actually see my screen? Yes. Sorry, my cursor? Yeah.
We can see it, yeah.
Yeah, so the vehicle mass times the speed, instantaneous, times the acceleration, plus if it goes uphill here, so the road rate is theta. For all roads of practical interest, sine theta and theta are the same thing. So here technically we want to write sine theta, but it's more or less the same to just write theta here as the angle of incline. Again, vehicle mass times gravitational attraction times the speed, plus and then some friction function essentially here, which could be some polynomial, for example. We'll talk about in the next slide what this means. And then I would get the fuel consumption rate instantaneously in time of this vehicle as some function of the instantaneous speed and the instantaneous acceleration and the instantaneous road rate that the vehicle is experiencing. Another class is empirical fitted models, where I still maintain this structure that I have my energy demand or fuel consumption rate is an instantaneous function of what the vehicle does in terms of a simple state space, namely just speed, acceleration, and theta. But then I use some fitted function to some data. And do some fitting here, like plotted here. And I could do this, of course, with models that incorporate gear shifting, which will then include essentially jumps here. So at some point, this is when the car will switch gears, and then the energy cost goes down at the expense of having less torque. Or I do models that in some sense average over the gear shifting, either by construction, carrying out this averaging, or by essentially just putting the fitted function and prescribing this to go through in an average sense. So I get continuous functions, possibly even convexity, either by construction or as a consequence. And the third class are really principal state-space models. So models where the vehicle state is not characterized by just its speed, profile and the road grade, but is really something where you have an additional state vector z here that is given by some nonlinear state space model here. Could even be discontinuous, so a mix of a hybrid of continuous components and discrete dynamic state space models, switching modes, hysteresis built in, so that the output, the fuel consumption rate, is something in terms of the state here, the system state, but that is a very, very complicated math. These models are, by construction, if you interpret it as just speed, acceleration, and road grade, non-local in time. So the fuel consumption rate at a given instant in time will not just depend on what the vehicle is doing in the moment in terms of its speed and acceleration, but will generally depend on all the internal state variables. So a real vehicle is of that type because it has a lot of internal states. And hysteresis effects built in, for example, in the gear choice. But the hope is, of course, or one question, if one were to approximate it, for example, by a local in time model, how good or bad would that approximation be? So real vehicles behave this way, but also, for instance, the software autonomy that we're working with in this project is of that type that you have a lot of internal state variables. And a vehicle is really characterized by a driver model, an environmental model here, but then also lots of internal components. It might be a little small to see, but lots of components that characterize everything that's in a vehicle essentially under the hood in there. So this is sort of the classes of models. And if one wants to start on the first type of model, namely modeling the physics, then one would start out by saying, okay, I have a force to overcome here. So the vehicle needs to overcome a force. If not, it will be slowed down accordingly, right? So the vehicle engine outputs a forward force, but it's facing a resistance force. And that resistance force is essentially whatever force you need to accelerate yourself, plus whatever force you need to overcome to go uphill. Could be negative, of course, if you're going downhill, plus whatever additional friction you're facing. And that friction then, again, you could model in a principled fashion, for example, by saying that I have a friction force component that's proportional to the velocity squared. That would be the turbulence air drag, and the air drag coefficient would be a fundamental parameter of the vehicle. But then also involving linear and constant effects in terms of which can model rolling friction of the tires. That's usually proportional to V. There's some laminar air drag components. There's some internal friction of components. Some could be constant, so that this can be absorbed into these terms. So one can see sort of this polynomial approach here as something that's just, of course, you use a polynomial if you know nothing else, right? But you could also see it as actually representing physical effects to leading order. So this is the force that's acting on a vehicle. And if you're traveling a certain distance to overcoming a given force, then if you multiply the force by the distance traveled, you get the work. And if you divide this by the time it took, then you get the energy, the power that you're doing. And therefore the power is the product of the force with the velocity. And therefore you get this whole expression up here multiplied by V, by the velocity V. So that's sort of the basic ingredient. And then, of course, you need to very carefully address with contemporary combustion engine vehicles, what happens if that power here is negative? For example, because you're going downhill very much, or because you brake, and you make your acceleration therefore very negative, for example. Then the power in general will be negative. And then you have to be careful that in general with combustion engine vehicles, you don't have any regenerative braking. So the heat, the energy just gets transformed into heat, is essentially lost. So therefore you essentially should max this out with 0, where this here could also be replaced by something that's more accurately modeling what would happen precisely in this behavior. But in to leading order, that is quite a good approximation actually of the behavior of the vehicle. Hybrid vehicles or electric vehicles generally have some form of regenerative braking, so that could also be involved here, but then it would lead to different behavior here with an efficiency of recuperation factor here. You also can look at this function here and say, okay, so what actually affects the power function here is the product of v with f of v. So essentially, you get a v cubed here at leading order when you do the power, and then you get a quadratic term and a linear term here, right? And then one can make arguments again that if you also want to model the fuel usage at idling that is coming in, and also potentially want to bring in a value of time into your optimization problem, in both cases, you will also get a constant factor here in the power, which results in a v to the -1 factor in the force. So again, this can all be done in a very principled way, and you can interpret these coefficients here either as coming really from physics, as being the air drag coefficient, for example, multiplied by the frontal area, cross-section area of the car, or of course as fitted parameters by fitting models of this type to data. In fact, the philosophy that you saw in the talk by Noor Kodari yesterday of having these functions that are fitted to the virtual dynamometer data, or for that matter to real dynamometer, generalize, have the philosophy that they generalize precisely this physics form, so that you have essentially some function here, power function fitted, that has this, exactly this form here of polynomial of 2⁵ in the velocity itself, but now with these coefficients fitted to the data. But it reproduces and mimics the form of the physics that you would get if you derive the physical principles, and then allow some generalized coefficients for the acceleration term here. This would be essentially this term here, this P1 would be playing the role of an effective generalized vehicle mass, for example, and then allow also for superlinear terms in the acceleration as well. Well, I will say a few highlights on what this means to have these superlinear terms as well, involving some road grade functions, and allow for the fuel consumption to be not exactly zero if the power is zero, but being some minimum value. Sometimes it's exactly zero if you have a fuel cutoff, and sometimes not. So this can also be modeled in these functions. Again, the framework that many of you have seen already that we do in this project is this autonomy framework, where we start with the autonomy framework that's non-local in time, has lots of internal variables. It gets exposed to a virtual chassis dynamometer. This leads to this semi-principled model that still is really modeling the physics of a vehicle, but in a time instantaneous fashion, but for example, has gear shifting and fuel cut in it. And then this gets fitted as a last step by a simplified model that then is continuous and convex. So you see here that these jumps that are present here in this model due to gear shifting, in fact, get replaced by a smooth convex up function. And this is a toolbox. Of course, you could use energy models at any of these hierarchy levels, but if you want to do optimization, we generally advise to use those here, which I hope I can highlight in 2 slides. So again, to recap, so the true vehicle energy, as well as the autonomy, is non-local in time. The idea is to approximate it first by something that's local in time, but incorporating gear shifts and other effects, and then to approximate it by a convex function that then yields these behaviors here that are still as close as possible to the model with gear shifts, but essentially average over them. And Noor provided some interpretation and rationalization for this. And again, the fitted models then that you get of this form in general here as it's written down. And here are some parameters for different vehicles that are fitted. You see that sometimes these parameters are 0. That is not by accident here. This is because we enforce that all these coefficients must be non-negative. And that constraint then sometimes makes them exactly 0 whenever the constraint becomes active. And the reason why we enforce this is a mix of physical arguments and the fact that we want to guarantee that those functions satisfy convexity properties and don't have local minima and maxima on this. So we're willing to take a little hit on accuracy of approximation for the benefit of getting these approximations here. But generally, the approximations are quite good on average. And the special case of this is the true physics, right? Modeling by physical principles, which is written here. So this is on the energy modeling, recapping again what we saw before. But now the question is, okay, when you have these different types of models and different structures, what does this now mean for conducting energy optimization? So again, we look at a single vehicle. We're not looking at traffic flow right now. We're only looking at a single vehicle, and we say, okay, we have a power function for this vehicle, and we have a given velocity profile. We don't have any cars ahead of it. There's no other constraints other than its own capabilities. So we have a velocity profile, and for a given velocity profile v of t over a time horizon from 0 to capital T, we have an energy functional that's essentially the time integral of the power function. where v dot here is the acceleration, right? The time derivative. So integrated the power over time is the total amount of work or the total energy that you needed to expand to travel that energy profile. So the simplest scenario again of a power function is just m times v times a plus this generalized friction function here, where the generalized force function f itself is of this form here, right? We start with with 1 over v as a leading term and go to v squared, so that the v times f function then is essentially a degree 3 polynomial. So that is the setup here. And what is important here, if I can draw your attention down to these figures here. So this is an example of the fuel consumption model of a vehicle that was fitted. This is not the final product, but this is some function that I took from one vehicle, the midsize sedan here. So you have on the one hand this function that is v times f of v, which would be essentially something that we then approximate by a degree 3 polynomial, right? Going through here like this. It's not plotted here, but that would be the approximation. But you see in reality, especially at lower speeds, the gear shifting is quite substantial and quite relevant in what's actually happening on a detailed level. And then you see that this is the behavior of this function that is the power function in terms of physical terms, or the fuel consumption rate in terms of if you actually talk about fuel. Fuel then would be in grams per second, for example, right? So mass of fuel per time, and that's the equivalent of a power here in physics. And likewise, then the force function, what would be the force in physical terms, would then correspond to the fuel per distance traveled. So that would be essentially without the v, right? Or this fuel consumption rate divided by the speed. So that would be grams per meter traveled. And this would be the equivalent. And you see essentially the 1 over v effect here, right? Coming in here. And then this would be another example of these functions. These functions eventually, if you went to much higher speeds, have to go up again because air drag becomes more and more important. But in these fitted models, this is at these speeds, not visible here. But again, this is not the final version of these models anyways. But this analogy between fuel consumption rate and fuel per distance traveled and the difference between them is exactly reflected between the power function and the force function. So you can use power and fuel consumption rate interchangeably and force versus fuel per distance traveled interchangeably in terms of your arguments. Now, if you minimize the energy, for example, say in the simplest setup, what if you travel at a constant speed, right? So if you travel at a constant speed, then your energy that you spend is just v times f of v times the time of your trip. And now you could say, oh, okay, now I want to minimize the energy. And there's already two different notions how you can say I want to minimize your energy. For example, I can say, okay, how should I choose my speed v, right, my constant speed v, such that I consume as little energy as possible over a fixed trip duration t? Or I could say something else, namely I want to say, how do I choose my speed v such that I travel a fixed length, right, a fixed distance? How should I choose my v then? And you immediately see that in the first case, it would lead to minimizing the function v times f of v, whereas in the second case, it leads to minimizing the function f itself. And of course, as you see from the shapes, this leads to very different answers, right? If you take this polynomial function, in the first case, the boss policy would be to stop, to not go at all. Whereas in the second scenario, because then you just have the C0 contributing, whereas in the second scenario, this function here you see from the 1 over v and the v squared here, it has a local minimum, and that would be your optimal driving speed, v star, for example. So it really matters what your setup is of the problem when you say you want to optimize energy. And one thing is, if you say that what actually is more reasonable is not, of course, coming to a stop. What's reasonable is what's your energy per distance traveled. Then you can also do that instead of expressing everything in terms of time. You can actually do a change of variables and rewrite everything in terms of the speed, which I call now u, just to avoid confusion, right? So u is when I say speed as a function of x. V is when I say speed as a function of t. So u as a function of x. And then by change of variable, you get a new functional e of u. I just use the same letter e just for simplicity. But then is this generalized or space-dependent power function g here, which then is given by the power function here, where the acceleration is u times w and then divided by u. This is some simple algebra by just the chain rule and change of variables formula. But then you get that the simple energy function here that we had before translates into that function g here. And now you see that instead of v times f of v, you now just have the f of u here. So it represents the fact that when you do a change of variable over position, then you get minimizing f itself rather than v times f out of this. So that's the first thing on how to set this up. The second thing is when you do optimization and you take a smooth function, a smooth energy function, then obviously this setup exactly leads to the calculus of variations problems that one has. So that's another thing, of course, that's important to highlight. So here, for example, written in terms of u as a function of x. So given a velocity profile over the distance that you want to travel, you have your energy cost function here, right? Integral from 0 to L over that function here. You could do it in terms of t as well. You just have to be more careful what your constraints are and what you want to minimize. And then with that simple model structure where that g function is just m times u times w, w being your u prime of x, which is essentially your acceleration times your speed, plus this f of u. And then you get your typical optimization problem, minimize from a set of feasible velocity profiles that are allowed, that the vehicle can do and are considered safe. Minimize the energy subject to, for example, some initial condition on the speed or not, or some terminal condition that the speed that the car should satisfy or not. When I say or not, it's down here. Whenever you don't choose to specify something, the calculus of variation induces a natural boundary condition that in this case would be just the partial derivative of the function g would be equal to 0. And everywhere in between, a necessary consequence of being energy optimal is that if everything is sufficiently smooth, that the profile must satisfy the Euler-Lagrange equations, which is the partial derivative of g with regards to u is equal to the derivative of the partial derivative of g with regards to w. Again, a nice exercise to carry this out for example, the very simple velocity function where the acceleration appears only linearly. That leads actually to the mw here. W is u prime vanishing, canceling out, and you actually get a degenerate equation with just f prime u is equal to 0. Whereas if you allow the acceleration also to appear in a quadratic term here, then you will get an actual second order PDE, which is more normally what one would expect, that you get a second order PDE, in this case, a nonlinear PDE with that coefficient function Q here. And this is a second order PDE. So if you have two boundary conditions, either prescribed or arising as normal conditions, then this would be a PDE that you can worry about, of course, the well-posedness of it because it's nonlinear. But in fact, in simple cases where Q of u, for example, is constant 1 or just a constant, this actually becomes something in the flavor of a Poisson equation that you have with some nonlinearity here on the right-hand side. But the differential operator is simple. And this here would be essentially the limit of Q going to 0, but it's a singular limit. It's a singularly perturbed problem where you just get f prime of u is equal to 0. So there's no time derivatives of u in there anymore, meaning as a consequence, the solutions that you actually get to this is that u is constant in time and its value is exactly the v star, right? The minimum value of the function f itself. So in other words, the solution that you get is always derived at a constant speed, which is the optimal speed. That, of course, then sounds in this degenerate problem, right? Really weird. What if I prescribe an initial speed that's not equal to that optimal speed that you get? And again, you sort of get what you ask for when you optimize energy. So this is the Euler-Lagrange equation, the second order PDE, or in that case where the energy is only linear in the acceleration, then you get this degenerate equation, as we said here. And now you have to ask what happens, actually, what do the solutions look like and exhibit? So without covering all the details, you also need to look at what happens when you have non-regenerative braking. So if energy is lost when this function here becomes negative inside here, and this means essentially that you don't allow it to be negative. You have a region then where it's 0, and the boundary of that region, that is essentially the curve corresponding to essentially the edge of having positive power versus 0 power. That is essentially exactly corresponding to taking your foot off the pedal and then coasting slowly towards 0, but not wasting fuel by braking. So that's, in some sense, you could call the 0 pedal curve. And that 0 pedal curve is exactly then parametrizing in the UW space. Again, remember, W plays the role of an acceleration, just being a function of x rather than a function of t, right? And this is just this function here. And if you therefore want to move down along this coasting to like 0 pedal coasting, so going down to zero speed without braking, then your speed profile would exactly be given by this zero pedal ODE. That's essentially given by this right-hand side. So that's how you would slow down. And you always have to slow down by this curve if you want to be energy minimal, because otherwise, if you were to brake, if you were to slow down more heavily, you would waste fuel. Yeah, you would waste energy and destroy energy, kinetic energy that's in your vehicle without any benefit for it. But otherwise, if you don't waste energy and always stay in the regime at most on this curve, then if the energy functional is linear in your acceleration, it actually means that you can accelerate as rapidly as you want. You will not get penalized because it gets translated into kinetic energy perfectly. And when you then slow down, it gets essentially you get it back right away, right? So at the moment, as long as you never brake, you get actually a perfect recovery of that energy, which one can make as an argument that you want your energy models to actually have a little bit of a quadratic term at least, right? A superlinear term in the acceleration, because otherwise you get that funny behavior. But in practice, it turns out that many of the fitted models are roughly linear in acceleration, which means you have that effect that when you have unsteady driving, this increases in an increase in energy, not necessarily, or not from the fact that you accelerate and slow down, as long as you don't brake, right? But actually just from the fact that you're not driving at your optimal V star all the time, okay? So, and then you see that if you want to construct the solutions, if you start at an initial speed that's below the target speed, V star, then you would ramp up according to a maximum feasible acceleration. If you start above, you would move down along the zero pedal curve. And also, of course, if you don't give a terminal condition that prevents you from going down, the energy optimal solution to the problem is one that at the terminal time exactly comes to a stop and you move down along the zero pedal curve. And if you want to avoid this, you have to actively work against it and design your problem that this does not happen. Okay, so there's a lot of really interesting structure in these problems. And the last point to be made here is that, okay, so the problem with smooth energy functions already is quite interesting to look at on a single vehicle. Now, what if you were to use an energy function that's non-smooth, for example, one that has these jumps due to gear shifting? And then again, first statement, of course, the Euler-Lagrange equations, don't use them for such a case. First of all, they're only necessary anyways. But second, they're only valid if your functional is sufficiently smooth. So then it makes sense to look more directly at the power function. Don't invoke the calculus of variations, just look at the structure. So again, simple situation where the acceleration appears linearly in the functional. So you have that V of f, and then you see if you take the integral, now I write everything in terms of time again. Again, because you can here. The key point is you see here another statement, another version of what I said before, namely that the acceleration, as long as you never brake, the acceleration is recuperated essentially when you slow down again. Is also reflected by the fact that this term here, the acceleration term, is actually fully integrable. So it's v times v dot. So that's just the derivative of v squared, right? 1 of v squared. So therefore, the first term, the acceleration-based term, just integrates completely to just being the difference of the velocity squared at the final time minus the velocity squared at the initial time. And all that matters for your energy actually is the time integral over this v-dependent part, right? Where you are in the velocity space. So now let's set up your problem that you actually drive a fixed distance L in a fixed time. So you specify both the distance traveled and the time. In other words, you specify your average speed, right? You constrain your average speed. For example, because you follow a lead vehicle that is going at that average speed and you don't want to fall behind and you don't want to crash into it. And let's say you also specify your initial and terminal condition to also being equal to that average speed. Then you can ask, now what is the optimal driving trajectory? Well, if you have a convex energy function, it would be drive at a constant speed v average, yeah, which would be that red dot here. But if you now take an energy function that has these jumps, then you see here that you could take a velocity profile that's not just at a going or constant speed, but for example, take one that half of the time goes at an increased speed, which is this point here, right? And because going at this increased speed, you just switch gear from being, this is first, second, third, fourth. So being, instead of being in fourth gear, right, just on the edge, you have switched down to fifth gear. in which you're down here, more fuel efficient, and then the other half to make up for the that you were too fast, right? You go after the other half of the time you go slower, and then you're here and you're also lower, right? You're in fourth gear now, but you're lower. So overall, you actually have a difference in the total amount of energy in some unit, doesn't matter. The ratio is 1.2. So you actually have a 20% mismatch between these two energies, if you really look at this. And that, of course, is first conceptually important of rationalizing what it means to optimize energy. And yesterday, Eugene and I had a quick chat in the question there. We said, hey, what if we put one of these energy functions into your RL framework and actually see whether it actually tries to exploit some of these things? That would actually be interesting to do. We haven't done it yet. But the other point, of course, that one could say now, and this is the key question here, okay, so now you have that mismatch of 20%. That's quite substantial. So how can you justify doing energy models that smooth out these jumps here? And there's two answers to this. One is that if you do something that explicitly exploit this, usually you don't want to cruise at these speeds, right? 12 meters per second. You're rarely in circumstances where you can really just cruise along at these speeds. So therefore, generally exploiting these gear shifts explicitly will be perceived as unnatural by the humans in the car itself, and also by the people behind you. And second, more importantly, we're interested in traffic, not just a single vehicle, and where these jump locations are is very different across different vehicles. And therefore, the idea is that averaging over many vehicles in that class, for example, midsize SUV, midsize sedan, will then smear out these jump locations as well. On an average, actually, a smooth convex function will do the right thing. Now, very quickly, lessons learned, right? So in energy optimization, the proper setup is one has to be very careful. Time versus distance in the denominator, what the constraints are in the terminal and initial conditions. But for a wide class of convex energy functions, in fact, the energy optimal trajectory is driving at constant speed, but not always. Okay, so one has to be careful. But that means that smoothing would be the right energy approach as well. You see it here written down, right? There's, depending on the setup, it's different scenarios that we're going to set up. Another important message: if the energy is only linear in acceleration, then the variations in velocity are only penalized by the function f itself, not by the acceleration, as long as you don't brake. If you brake, of course, then you lose a lot of energy due to that effect as well. But that's another interesting fact. A non-convex energy yields one can easily construct examples where you get non-constant optimal speeds. And some of these, many of these issues have been seen by setting up the reinforcement learning procedures and look at them. And the final comment I want to make is that, well, you see the non-zero road, great. I don't need to say this. So what's important is that all of this is the single vehicle so far. And again, we need to remind ourselves what's the actual problem. So we do that in a forward fashion. We optimize mostly for, we want to smooth waves, but strictly speaking, if I wanted to set this up, that I would say would be sort of the model problem. And it resembles a little bit what the RL team has been doing lately, right? Which is you have your AV, but it has a lead car in front of it. And then you have an immediate follower of the AV and other followers behind. Those are the human cars. And you want to actually choose your AV speed such that the energy of all the followers is minimized collectively, subject to A, of course, the capabilities of the AVs, B, that the gap to its leader remains acceptable, whatever that means, right? And 3, that the annoyance function A of the AV's immediate follower stays between a critical threshold where you have some model, and this is now human behavior, so Katie is needed here, would be needed, right? To model the annoyance evolution model by some function that makes it increase and some other term that constantly relaxes it to 0, and then the balance between those matters. And this function depends on how the AV is perceived to drive with regards to the lead car. Right? So that's what one actually should do. I don't know if one can do any closed form studies here, right? Because it depends now on many models, including car following models, but that's really actually the problem that should be solved. But I think many of the insights of the single vehicle case structurally are actually quite important for going forward and really seeing what can be done. But it's also a cool thing where one can not just do experimental work and simulation work, but I think also some real interesting math questions come in here as well. Thank you very much.
Okay, thank you so much, Benny, for that that comprehensive talk. Are there any questions?
I have a quick question about the slide right before. So what you said about the contribution of acceleration to the energy means that Actually, if we had an energy function that is superlinear in the acceleration, is that, if I understand correctly, even a perfect electric car that will recuperate 100% of the braking will still be penalized by acceleration?
Yes, that's exactly right. Yep.
Okay.
And the amount of the second
interesting.
derivative is exactly giving you the amount. But yes, in phase space, essentially you drive circles, right? If you have a sine wave, right, it's ellipses in phase space that you move. And when you have linear in acceleration, but sort of you are at a valley in the force or v part, right? Then what penalizes your ellipses will be going left and right in the v direction. But in the a direction, it integrates out, right? By this expression here, right? And whenever you have a superlinear term in A, then this bowl shape essentially, right? It's always bowl shapes that matter, right? So the bowl shape in the A direction would also add to the penalization. But in some of the fitted models, so in the fitted models that we have on the earlier slides, we have a quadratic term in there. But sometimes the coefficients are comparatively small. So back of the envelope calculations actually indicate that done also by the IL term, that the loss due to, if you have small amounts of variation, that you don't break, right? You're just going up and down by using the gas pedal, for example. Then the loss due to acceleration being variable is in fact smaller than the loss effects due to velocity. But everything is dwarfed by what's happened when you brake. What's happening when you brake? So in other words, when you accelerate, you consume a lot of fuel, but you make up for it when you slow down, as long as you don't brake, right? That's the key point. So the real wasting happens during braking. And since in strong waves, people usually brake, right? That's what dominates everything. Yeah.
Thank you.
All right, are there any more? Actually, I have a quick question, Benny. We talked about the power being linear with respect to acceleration. Sometimes there's a power was linear in acceleration, I think you showed. Yet we know that based on the complicated details of all of the different friction terms, that there should be some sort of, quadratic friction term in velocity. Does that mean that driving over the optimal speed is always worse than driving under slightly the optimal speed?
How does acceleration come into that question?
My sense is that you would penalize, one could think that maybe you'd penalize equally for driving a certain amount over the optimal speed, but as you would penalize for driving under the optimal speed. But the asymmetry is that the friction terms are higher in the one case and lower.
Well, first of all, in terms of the V terms, right, it depends on what these coefficients are that you get, right?
That's true.
So if you travel a fixed distance, right, and you want to choose a velocity profile, you have the constant reference state or something, and then you have something that's variable, right? Whenever you're something variable and you say that it's non-optimal, right? So it has more energy than driving at a constant speed at the same average distance time or something or not. Well, it depends on also whether you fix the time, right? Fix the average speed or leave that open, right? But if you compare this sort of with driving at that V star, right, the optimal speed, which, by the way, sometimes it's way too low for some vehicles, right? It depends on the vehicle, but sometimes you cannot drive at the V star. It's just socially unacceptable, right? But if you are near that one, then if you go up and go down, which one is giving more? I think there's no general rule I could make based on what I've seen. It depends quite on what these coefficients are actually. Yeah.
Sure. All right. Any more questions that anybody thought of? Well, this
Good,
is
then
the
let me
last
use
talk.
quickly that opportunity for everybody who's still left to thank all the organizers for this workshop, and everybody is now giving an applause for all the organizers. Even the last Mohicans who are still up at night in Europe. So it's great to see everybody here. And with that, thank you, John. We had it back to you.
All right. Thanks. So this is the end. Are there any closing words that anybody wants to say? I mean, the ones we just heard were great.
Let me just thanks again everyone for participating, the organizing committee, scientific committee, especially the Europeans being here at late night. Paula is heroic, being from almost sleeping but still resisting, so that's great. Thank you all, and looking forward for the Circles workshop number 2, hopefully next year around the same time. Thank you all and enjoy your weekend. Well
Thank you very
deserved.
much.
Bye.
Thank you.